Remind you where we were. So recall. So we've started introducing the states of a quantum field theory, and we had a ground state. So there was the ground state 0, which is defined by the fact that it's annihilated by all the annihilation operators, an infinite number of them. And we then started looking at the excited states. So the first excited states, which we then interpreted as one particle states. That's what you get by acting by a single that's great, thanks Tibra. It's what you get by acting with a single creation operator on the ground state. And we started looking and convincing ourselves that this does indeed have all the properties that we would expect from a single particle state. So in particular, the momentum of this, the energy of this particle, we learned was p squared plus m squared. So it's got the energy that's expected of a relativistic particle of mass m with momentum p. The momentum of this particle, where this is the operator that you get by considering the conserved quantity that arises from translational invariance of the theory. So this just spits out the momentum p, so it's suggesting that it does have the right momentum. And finally, we also looked at the angular momentum of this particle when it was sitting there at rest. And we found that it had 0. It was 0, which we interpret as the fact that this is a spin 0 particle. Okay, so let me just stress this fact again. When you're first learning quantum mechanics, you're told that, because of miracles of the Lorentz group or something, particles can have this extra internal angular momentum which adds to other angular momentums, and and it's called spin. But here we see that what we're calling the spin of the particle is really just coming from the angular momentum operator. It's computing the angular momentum of the entire field, and we're evaluating that angular momentum on the one particle state. And okay, there's nothing that interesting so far because it's just giving 0. But we'll later see that we do exactly the same thing. We compute the angular momentum of a one particle state, and it's going to spit out a half for fermions, or 1 for photons, and so on. Okay, so there's nothing different about the spin from other angular momentum. It's all contained in the angular momentum of the field. Okay. We also saw that these were bosons, just because these A daggers commute with each other. So this is the first example of the spin statistics theorem. It's not something that we've put into the field theory. We're just finding that naturally we have spin 0 states that are bosons. And next week we'll find that we naturally get spin half states, which are fermions, and so on. Okay. So are there any questions about this? No? Okay, so there's a few things I just want to sort of follow up on with this today. So the first is important, but it's a little bit fiddly. It's a question of the normalization of these states. Okay, and it's to do with this point that we haven't got manifest Lorentz invariance. We believe the theory is Lorentz invariant because it came from a Lagrangian, which was Lorentz invariant. But we had to go to the Hamiltonian picture, which involved picking a time, and then we look at these states, and the states are just labeled by 3 momentum, and so we might just be a bit worried about things. And it's going to turn out that although these are the right states to look at, there's a normalization that we could put in front of here, and we're going to have to choose a slightly different normalization than the naive one, which is just arisen, which is 1. Okay. So the vacuum is normalized in a sensible way. it just has unit norm. But this then means that the one particle states obey the following. Okay, so just to see how we get that, you put in Q here, which has an A dagger Q. The bra vector P has an, after you flip it around, has an A, and then you just commute the A, P, and the A dagger Q past each other. That gives you the delta function. And then as soon as the A gets here, it annihilates what's left, which is the vacuum, and similarly the other way. Okay? Okay, so we've got these kind of, these aren't terribly good states in the Hilbert space, but they're not terribly good in the way that's familiar from quantum mechanics for plane wave states. They're not normalized to be 1, but they have this annoying delta function normalization. But that's the same issue that we've come across in quantum mechanics before. The problem here is a question about Lorentz invariance. And in particular, it's the question about whether this quantity here is Lorentz invariant. Okay, now it's not obvious that it's Lorentz invariant because it's got 3 vectors there and not 4 vectors. And it turns out that it's not Lorentz invariant, but if we multiply it by something, it will be. So what I'm going to do now is show you what the Lorentz invariant delta function is, and then we're going to multiply the states accordingly so that we get some Lorentz invariant quantity on this side. Okay? Okay, so here's the first thing I'm going to prove, just to try and figure out what is a good Lorentz invariant delta function. And my claim is that the following measure over 3-dimensional momenta is a Lorentz invariant measure, where, remember, the energy here is the energy of a relativistic particle. Okay, so let me just prove this. And the trick is just to start with things that we know are Lorentz invariant and then go on from there. So the first statement is that it's clear that the integral over all of Minkowski space is Lorentz invariant. Okay, everybody agrees with that? Yeah.
Is conservative you're saying? Or no, wait, yeah. Oh, this is D4. Okay, yeah. Sorry.
Yeah, it's D4. Yeah, not D3. So that's the first statement. The second statement is that for a particle of mass m, the following dispersion relationship is a Lorentz invariant statement. Plus. And in particular, so there's 2 solutions to P0, one with a plus sign, one with a minus sign. But picking which solution we're on is also a Lorentz invariant statement. You want to square on? Yeah, sorry. Thanks. So if I put a delta function in here that restricts me to be what's called on mass shell, which means that I only consider I integrate over all 4 momenta, but I only integrate over those 4 momenta which obey the relativistic dispersion relationship for a massive particle. This is also a Lorentz invariant measure. Okay, but remember what happens when you integrate over something with a delta function, which is a function of the thing you're integrating over. For your troubles, when you impose the delta function, you pick up 1 over the derivative of that function in the measure. So this is equal to the integral of d3p with this 1 over 2p0 here. This 1 over 2p0 is coming from differentiating this function of p0 and then doing this p0 integration. Okay. Yeah.
Maybe you just explained that, if so I don't quite understand how the d4p became a d3p with that delta.
I did the integration over p0. And I did it using this delta function, which meant that I only picked up p0 when p0 was equal to EC.
Okay.
Yeah. But then because it's not delta of p0 minus something, but p0 squared minus something, I pick up this thing sitting on the bottom. Okay, so if you want to integrate over 3 momenta and not 4 momenta, the way you do it in a Lorentz invariant fashion is you have to put a 1 over 2 times the energy, the relativistic energy of the particle. Okay, so an obvious corollary to this is that the Lorentz invariant delta function over 3 momenta is you take the delta function, then you multiply by 2 times the energy of the particle. Okay, and the proof of this is just that this is Lorentz invariant, and so there's the Lorentz invariant measure, and we multiply by the Lorentz invariant delta function. And that's what gives us 1. And 1 is obviously a Lorentz invariant number. Okay, so this is, a little bit fiddly and a little bit annoying, but still we have to go through it. So if you want to integrate over 3 momenta in a Lorentz invariant fashion, you've got to divide by the energy. If you want a delta function over 3 momenta in a Lorentz invariant fashion, you've got to multiply by the energy. So this is Lorentz invariant and this is Lorentz invariant separately. Okay? So going back to where we started, this means if we normalize our states, then the overlap of these new normalized states gives some Lorentz invariant quantity.
So there's no difference between E sub p without a vector and E sub p with a vector, right?
Yeah, no, I've not been careful, but there's no difference precisely because E subscript with a vector is the square root of p squared plus m squared. But you're right, I should be careful. What do I do in the printed notes, do you know? No vector? There is an arrow. Yeah, okay. Everywhere there's an E sub p, I should be careful because of what I'm going to say now. But everywhere there's an E sub p, you should probably put a vector then. But there's no difference between them. Yeah.
So you're dropping the vector to indicate a properly normalized state?
Good. So let me stress this because it's a very subtle notation choice, and I'm bound to make mistakes when I write things on the board. So be aware. The difference between this vector and this vector is just that I didn't write a vector here, I just wrote a p, whereas here I've got an underlined twin. Okay. So the difference between the two states is just this normalization factor. The fact that there's no twiddle here is supposed to indicate that this is the state that's normalized in a consistent fashion with relativism, meaning that what we get is a Lorentz invariant delta function on the right hand side. Okay. But it's a subtle choice of notation, and perhaps not the best. It's one that I think is fairly standard. Okay. So this means relativistically normalized. It's the same state, you just multiply by a factor of the A. Okay, so I'm going to have to try to be careful to make sure that there's a distinction between these vectors and these vectors. Mostly we'll just see these vectors from now on. Okay, so are there any questions about this? It's fiddly and annoying, but we've got to go through it. Okay, so a few more bits and pieces that I just want to introduce you to. We went through the real scalar field yesterday and quantized and found how particles arose. So now I'm just going to do exactly the same thing, but for the complex scalar field. Okay. Now, as the complex scalar field is made of two real scalar fields, you might expect that what we're going to get are two different types of particles. And that's exactly what we'll see. So consider the Lagrangian. I'm going to call this capital M, not because it's different, but just because later I'm going to have real scalar fields and complex scalar fields interacting together, and so I'm going to have two M's. So I'll just call this capital M for now. I said this before, when you have complex scalar fields, there's typically no factor of a half sitting here or here. Okay? It's because when you figure out the equations of motion, so Euler-Lagrange equations, you can treat psi and psi star as independent variables. And you find and then just the complex conjugate as the other one. Okay, so we want to quantize this in the same way we quantize the real scalar field. What do? We write down a mode expansion. So we have the field psi as a function of x. and we're just going to expand it in some Fourier basis. So we have the mode expansion psi of x Okay, so it's exactly the same as for the real scalar field, but for the real scalar field, I had A and A dagger. Sorry, I should have put a dagger on here. For the complex scalar field, I'm going to have B, and I'm just going to call this C dagger. Okay, so why isn't it A and A dagger? Well, having A and A dagger meant that the object on the left-hand side was Hermitian. Somebody asked this question, is A dagger the dagger of A? And the answer was yes. So now I've got a complex scalar field. There's no reason why this should be the dagger of this. And so I've just called it by a different name. Okay? And the fact I picked the dagger here instead of not a dagger, that's just a choice that will be useful later. We can also compute the momentum. Of course, let me just say this, if I write down psi dagger, I pick up a dagger here, a minus sign, no dagger here, and a plus sign. Okay, you just take the usual Hermitian conjugate. Psi dagger will be the quantum operator associated to the real field psi star. Yeah. Maybe I'll just write that. Okay, then we've got Momenta. Yeah.
I don't quite understand the distinction between psi star and psi dagger.
By star, I just mean that it's a typical C number function. By dagger, I'm emphasizing that it's an operator.
Okay.
Yeah. So it's not just complex conjugation because it's really an operator. So now it means Hermitian conjugate.
Okay, because now we're talking about the promoted.
Now these are quantum fields, operator value fields. Yeah. So what's the momentum? Well, the momentum conjugate to psi dot. Sorry, the momentum conjugate to psi is psi dot star. So you get this flip going from the momentum conjugate to psi has a star there. Okay, so again, you just do a mode expansion. And just like for the other case, you can really think of these two expressions as the definitions of B, B dagger, C, and C dagger. Okay, we're just rewriting the variables. And there's one for pi dagger that I'm not going to bother writing down because you just change this and put this to a plus. Okay, so the commutation relations. Okay, the commutation relations for this are that psi doesn't commute with pi, its own momenta, when x is equal to y. Sorry, there should be a y there. Okay, everything else is vanishing. In particular, psi commutes with pi dagger. Okay, so you can do this tedious exercise where you figure out that given these definitions, this commutation relation is equivalent to these commutation relations with everything else. Given the definitions that I've just given you, let me see, what's the easy way to go? Yeah, I think it's easier to go this way, actually. And you have to invert these and anyway, the homework exercise for this weekend is basically fill in all the gaps that I've left in these lectures. So whenever I've said, if you plug this in, it'll work, just check that it works. There's no point doing it on the board because it's really tedious. You know, it's always just plugging in mode expansions, doing the integral over x, finding a delta function, using that delta function and getting the right-hand side. But just, you know, do it over and over again and it'll be helpful. As Callum said, he would love to grade this You know, there's this movie from the 1980s called The Karate Kid. We've seen this where Ralph Macchio wants to become this ninja warrior, and so he goes to Mr. Miyagi, and Mr. Miyagi makes him spend all this time washing fences and cleaning cars, wax on, wax off. You guys seen this, or this is just not your generation? So these exercises are kind of like that movie, you know, and it's not obvious why you're doing it, but you keep working and working, and by the end you'll be, you know, some quantum field theory ninja warrior. So that's the goal of this homework exercise. Okay, so what do we have here? It's a complex field. We've got two creation and annihilation operators, B's and C's. We could work through exactly the same thing we've gone through. You find that each of them will give you a particle of mass capital M and spin 0. Okay. Each of mass M and spin 0. Okay, so why am I going through all this? Because it looks trivial, right? I had a complex field, but okay, a complex field is exactly the same as two real fields. So of course I've got two particles of the same mass. I could have just expanded out. The complex field equals 1 over the square root of 2 phi 1 plus I phi 2. And it would have been just reduced to the previous problem. So the reason I'm telling you this is because of this conserved charge. Okay? So the theory has a conserved charge. And the conserved charge we worked out maybe yesterday, maybe the day before. Psi minus psi star psi dot. Okay. If I write it in terms of the momenta instead of the psi dots, it's pi psi minus psi star pi star. Okay, so now comes one of these tedious exercises that you're going to do over the weekend. Plug in the definitions of pi and psi in terms of the mode operators, the b's and the c's. Do the integral over x. There'll be one of these annoying infinite coefficients that you'll throw away by normal ordering. Okay. So after normal ordering, we'll find q is equal to the integral of d3p so you find the following expression. But we wrote down this expression yesterday as well, where we had a's and where the b's and the c's are. This is the operator that counts the number of particles in a given state. Okay, it's the number operator of the harmonic oscillator. But now it's the number operator for momentum p, but then you sum over all possible p's. So this will tell you how many particles you have in your state if your state has a fixed number of particles. So this is nc minus nb. Number of C particles minus number of B particles. Okay, so big deal. We've got an operator Q, which is the number of C particles, not minus the number of B particles. Now, in the free theory that we're considering, the number of particles doesn't change. You know, nothing interesting is happening. In the real scalar field, the number operator n commuted with a Hamiltonian that told us the number of particles doesn't change. In this theory, nc commutes with the Hamiltonian, and nb individually commutes with the Hamiltonian, and the number of particles doesn't change. However, very soon we're going to come to interacting theories, where these particles actually bounce off other particles and do interesting things. When that happens, neither nc nor nb will be conserved. So they will change under the dynamics. They don't commute with the Hamiltonian. However, this quantity q, which is the difference between nc and nb, will continue to be conserved as long as that symmetry that rotated the phase of psi is a symmetry of the Lagrangian. Okay, that's what we've seen. Symmetries imply conserved quantities, and this is the conserved quantity for the phase rotation of psi. And it will be there in any Hamiltonian you write down as long as that Hamiltonian has the symmetry. So Q commutes with the Hamiltonian, which is telling us it's a conserved quantity. And this will continue to hold in interacting theories. As long as they have this symmetry. In fact, let me say this a slightly different way. Remember that when we computed this charge in the classical theory, it didn't depend what the potential was. You know, it didn't care about the potential. It only cared about the kinetic terms. You can see that here. There's no m's that appear in this. So it's going to be exactly the same object, regardless of what the potential is, and regardless of what the interaction is. It came from the symmetry psi goes to e to the I alpha psi. Yeah. Okay. So there's words that we have for the fact that the number of for the C particles and the B particles, and the fact that their difference is conserved even in interacting quantum field theories. And the word is antiparticles. So we call one of these particles a particle and the other one the antiparticle. Okay? And as we've seen, they both have the same properties. They both have the same mass. They both have spin 0. They're also going to carry other quantum numbers that are the same when we come to introduce other quantum numbers. Okay. So we interpret B and C as particles and antiparticles. And then Q is equal to the number of antiparticles minus the number of particles is conserved. Okay, so you get distinct particles and antiparticles when you have a complex scalar field. When you've got a real scalar field, we only got one particle, and the interpretation there is that that particle is its own antiparticle. So for real scalar fields, okay, and typically in a relativistic quantum field theory that's interacting, there's no way to have the number of particles that come from a real scalar field to be conserved. For particles, its own antiparticle, it can just annihilate with each other. And we'll see that usually that's what happens. If you have relativistic interacting theories with real scalar fields, the particles from the real scalar field just don't hang around that long. They typically annihilate with each other. And it's because there's no conservation rule protecting them. Okay, questions about this? Yeah.
Is the E&M field, is that a real scalar field?
No, it's going to be a different kind of field. It's called a vector field.
Oh,
You know, it has a little index on it because it's a vector and it rotates. And it comes with all sorts of wonderful subtleties in trying to quantize them. So this will be what we do in the third week. Let's look at that. What are particles in nature than the scalar fields? And the Higgs is the one we haven't found. But quantum field theories aren't necessarily just to describe fundamental physics. They describe physics on lots of length scales. So, for example, mesons, a very good example of scalar time mesons, which you can model as a field theory where there's a meson field and you quantize it and it gives you a little meson.
Yeah, I was just wondering, does the fact that you get particles and antiparticles in the complex scalar fields, does that have something to do with the relationship between complex conjugation and time reversal? Because
I think no is the answer. Yeah, why do you suspect so?
Because I once read something about an antiparticle being can be looked at as a particle propagating backwards.
Okay, good. So these field theories will have invariant under 3 discrete symmetries. Let me say it again. There are 3 discrete symmetries: time reversal, parity, which is sort of reflection in the mirror, and charge conjugation. There's a theorem that says that any decent relativistic field theory has to be invariant under the combination of all 3 done together, but not necessarily under any individual one. And the standard model is a perfect example of a theory which is invariant under all 3, but not under any individual combinations. Now, it's true that under all 3 of those, you get charge conjugation and time reversal, and particles turn into antiparticles. And this was one of the ideas that led Feynman to develop Feynman diagrams. And we can talk about this when we come to the Feynman diagrams. There was another question.
Yeah, from the way phi was defined, the field operator phi was defined, you choose C to be any operator, and there's nothing that will stop us from taking C to be equals to D.
Oh, but the thing is that would be giving an extra restriction that isn't there. So if C was equal to B, the field psi that we had would be equal to its Hermitian conjugate. Psi would be equal to psi dagger.
Yeah.
But that's not correct. It's coming from a complex scalar field, and so we don't want to impose that restriction. That restriction should only be imposed on real scalar fields, which turn into Hermitian operators. We don't want psi to be a Hermitian operator. That would be effectively saying that it was real to begin with.
If by chance I can put C equal B, then I have Q equals 0.
Yeah, so what would that mean? If you're... you shouldn't really think in terms of putting C equal to B, because they're different operators. You know, that would be like in quantum mechanics saying, we'll put X equal to Y. They're operators, so what does that mean? You could look at states whose eigenvalues under this operator was the same as eigenvalues under that operator. That makes perfect sense. In that case, these are states that have equal numbers of antiparticles and partons. Other questions? Okay, good. So what we're going to do now is try and push forward and start making things look a little more relativistic again. Okay? So, I've been stressing this. We start from a relativistic Lagrangian, really just to define our classical theory. But then to do this kind of canonical quantization, we're obliged to first go to the Hamiltonian formulation, and that breaks Lorentz invariance. At least it means that Lorentz invariance isn't obvious within the equations we're working with. We still hope that the theory is all Lorentz invariant underneath, and we're now going to see that, yes, that's indeed the case. Okay? So the big way in which the theory doesn't appear Lorentz invariant is in the difference between space and time. So in particular, at the moment, the operators depend on space. They're labeled by spatial position. So we have a different operator at every single point in space. But the operators don't depend on time. Meanwhile, the states they're not states that depend on space. We're not thinking of them as wave functions over space. They're something much more complicated. They're sort of defined over space as a whole. They're wave functions over the space of fields over space. Said another way, they don't really depend on space. But they do depend on time. They're the things that are evolving as time goes on. So that already sort of is a separation that's perhaps not ideal. But we know exactly how to change this. Because in quantum mechanics, we've got the Schrödinger picture and we've got the Heisenberg picture. And if we want a formulation in which the operators depend on space and time and the states don't depend on time, then that's very easy to do. We just go to the Heisenberg picture. Sorry, say that again?
So if we're going to build the observables later out of the fields, then why don't we want the fields to be Hermitian operators?
Oh, so they, there's not any subtlety here. If I'm in quantum mechanics, then X is a Hermitian operator and Y is a Hermitian operator. But for certain situations, it might be useful just to consider Z equals X plus I, right? Just complexify the plane, and you can always decompose it back into Hermitian operators afterwards. So that's really all that's going on here. We've got two Hermitian operators, call them phi 1 and phi 2, and it's just useful to combine them into a field phi 1 plus I phi 2, simply because it sort of highlights certain aspects, like C. But at the end of the day, you're right, everything we're going to be doing is going to be some Hermitian. This, for example, is Hermitian. Yeah, so it's not different from quantum mechanics. Anyway.
Oh, yeah, that was pretty much what I was going to say. The basic idea, right, is that our fundamental operators are the phi's and pi's, and all the observables are built out of those.
Yeah.
Okay.
Okay, so let's just make this shift to the Heisenberg. So at the moment, our operators phi of x depend on space, but they don't depend on time. So we can change this just by working in the Heisenberg picture. Okay, so what's the Heisenberg picture? Remember, for any operator, so this is true in any quantum mechanical system, quantum field theory system. So this is the operator in the Schrödinger picture. And this is how we define the operator in the Heisenberg picture. Okay, and then the equation of motion obeyed by the Heisenberg, the operator in the Heisenberg picture is just that you commute H and O. So is this familiar? Did Malcolm cover this stuff? Yeah. Is that question? Ah, good. Okay, so here's one of these exercises you should just do over the weekend. Check that using this, the operators for the real state field, they Okay, so how are you going to do this? You're going to take phi, you're going to use the mode expansion, as always, because that's telling you how phi is depending on space and time. Well, this is telling you how phi is depending on time, and then you plug into here that mode expansion is over A and you just work through it. So what have we got? We've got the... So here, of course, I mean, in the Heisenberg representation, whenever there's a dot, it only makes sense. Okay, so this is quite nice. Just by going to the Heisenberg picture, you can check that the field phi obeys a Lorentz Invariant equation. It obeys the Klein-Gordon equation, which is what the classical field that we started with. This is the Klein-Gordon equation. But let me stress this again. Phi is not the wave function. Okay? It has nothing to do with the wave function. Phi is now the operators over space. So this is an operator-valued field over space and time now, where the time has come in because we're in the Heisenberg picture, and it has to obey this equation. Okay? Yeah.
Earlier you had that pi was the time derivative of phi star.
Mm-hmm.
Were we in the strip?
Oh, sorry, no, this is for a real scheme.
Oh.
If you did it for a complex scale, you'll still get the star. The star will still appear here.
So we're in the Heisenberg picture.
Earlier.
Or was that,
Oh, earlier, sorry, that we were in the classical theory.
okay.
Yeah. So earlier I was. I think I maybe said it too fast. I did. So we want to know what the momentum is. How do you do that? You take the classical Lagrangian, you differentiate. Whenever there's a Lagrangian, we're basically in the classical theory. Yeah. And then it was the next line on the board when I expanded the quantum theories in terms of operators.
But if we already have this time dependence, why are you making a distinction?
No, so in the classical theory, the fields are a function of space and time, and obey certain equations and have certain relationships between them. Then we quantize, and as soon as we quantize, the operators stop depending on time because we're in the Schrodinger picture. And now we've managed to put time back into the operators by going to the Heisenberg picture, and we find that actually in the Heisenberg picture they obey the same equations as in the classical theory. Sorry, I wasn't really clear. Is that clear to everyone? Does somebody just want to ask me the same question again, and then I can repeat it again? It'll be clear. Yeah.
Here you quantize.
Yeah.
Right? But then here you still take the time with that quantized thing.
Ah, good. So not. Yeah, I was just too quick. Yeah, so the question is, this is going back to the case of the complex scalar field. I wrote psi equals and then some mode expansion, B's and C's. And then I wrote pi is equal to the L by the psi dot. Psi dot star. This is true in the classical theory. And then I wrote pi equals, and then a mode expansion. B dagger minus C. This is true in the quantum theory. So strictly speaking, there shouldn't be an equal sign between these two equations. I maybe put an equal sign on the board. Sorry, so there's a conceptual difference between this calculation and this calculation. I didn't stress. Thanks.
So how do you get pi is equal to or b dagger minus c from?
It's really just in the same way as I did in the harmonic oscillator, which is, I kind of pull it out my ass. It's a definition of what B and C and B dagger and C dagger are in terms of pi and psi.
Okay. Yeah,
right?
yeah.
I could have written anything. This is the thing that I know is going to help solve the equations.
Yes, I didn't realize that you had enough degrees of freedom.
Yeah, I got two complex objects on the left-hand side, psi and pi. Two complex objects on the right-hand side, C and B.
So you chose it like that because you knew it would work?
Sorry, say again?
You chose it like that because you knew it would work?
Yeah, because somebody solved the harmonic oscillator 80 years ago. Okay. Okay, so the next thing I'm going to do is write down the mode expansion for phi in the Heisenberg picture. So you want the mode expansion for phi of x comma t in the Heisenberg picture. So until now, until this board, phi was only a function of x, but now we're in the Heisenberg picture, it depends on both x and t. What we need to do this is the following results. Right. Let me just check I got my minus signs right. Yeah, thought not. Good. Plus. Okay, so why do I need these results? It's because phi is equal to integral of a plus a dagger. And to go to the Heisenberg picture, I've got to take phi and sandwich it between e to the iht and e to the minus iht. The only thing on the right-hand side of that equation are the a's and a daggers, which don't commute with h. They're the operators. So I'm going to find on the right-hand side things like a sandwiched between time evolution operators and a dagger sandwiched between time evolution operators. Now, why is this result true? It follows from the fact that the commutator of h in a is equal to minus a, and h in a dagger is equal to plus a dagger. Joe?
So way back when we were solving the harmonic oscillator, we had a time dependence in that. And if you'd left your time dependence in your classical solutions for the field, you would have had the e to the minus I omega t's in there. So is that cheating? Would it be cheating just to take that classical field, which depends on x and t? And
you mean solving the Heisenberg operator in the Heisenberg, solving the harmonic oscillator in the Heisenberg picture?
Well,
and then just carrying that over?
We were just solving for the classical field. And then we have everything in terms of classical field, and then we quantized it, and we dropped the time dependence. If you didn't drop the time dependence and quantized it anyway, then you get the same answers. And I just want
is that the same as just quantizing in the Heisenberg picture?
Well, it might be. This is what I'm wondering. I just want to know if it's cheating or not.
I'm not sure, but it's a question that we can ask within the harmonic oscillator itself. We don't have to go to field. Okay. So we can just check afterwards. Okay. So what do we get when we do this? We get the following. More annoying notation. If there's an x without a twiddle underneath, we're in the Heisenberg picture. If there's an x with a twiddle underneath, we're in the Schrodinger picture. Okay? Okay, what's the difference with what we had before? The difference is there's no twiddles under this, and the difference is these minus signs have flipped. So why have the minus signs flipped? It's because we're in the Minkowski metric where p dot x is e times t minus p dot x. Okay, so the e dot t is the new thing that's come from here. Sorry, that's when the e is, it's not independent, it's fixed in terms of p. It's the square root of p squared plus m squared. Okay, and this minus sign then cancels that minus sign and gives us back the original part from the Schrodinger picture.
Notational question. Does that notation of dropping the vectors decoration on X, is that why you dropped it on the exponents from the time evolution?
Yeah, basically this is now a field that depends on space and time. And here's the space and time. And you can check that this obeys Klein-Gordon equation.
A notational question. Before in the exponents you had been writing
just the x, right? And that's because we were in the Schrodinger picture. Yeah. Joe, I think this answers your question. This is the solution to the Klein-Gordon equation of the operator in the Heisenberg picture. It's exactly the same thing we had for the classical thing. So you could have just jumped straight there, but I don't know how comfortable you would be with that. But
why do we choose our vector signature like this if all it ends up doing is flipping all our signs all over the place whenever we have to add time?
It's basically because energy is more important than momentum to a particle physicist. And so that's what you want to be positive. But with this metric signature, the form momentum squared is always greater than 0. For a relativist, it's typical that space is more important than time, and you often use the other one. When I teach string theory, I use the other signature. Count.
Just about Joe's question, if you had jumped straight to this without going back and forth in the Schrodinger picture, what would you have written down for the commutation relations?
Yeah, good. Now, I think that's exactly the right question. Yeah.
Does that make sense?
So I'm going to write down the commutation relations now, and there's a subtlety. And yeah, I think you're exactly right. The subtlety is what you see by going by the Schrodinger picture and doing things properly. Yeah, thanks. Eric.
Yeah, sorry, just one other little question for the notation. Is there any reason why we still keep the twiddles on the P's for the A's?
Yeah, so they're and I haven't changed these is the real reason. Let me just do an aside. I decided not to introduce this notation because it's basically not relevant. But remember that, because I've confused you enough with dropping twiddles. So remember that the difference between this guy and this guy is some relativistic normalization factor. Some people define a similar object, AP, which, when acting on the vacuum, will create this with this normalization. So it's AP. Yeah. Okay. So I haven't defined that, and I'm not going to change this because if I did, I have to change my factors of square roots of 2e's here. I don't think I mentioned this in the notes, or I may have just mentioned it in passing. Okay. So some people will define this. I don't know who, but yeah, Tibor.
If you have that square root of then that will be a scalar density or something like that.
I don't think so, because it's not it's not square root of g or something like that. It's just a number.
Well, E is not really a scalar. I mean, it's a component of a vector. That's why we.
It's the component of a four vector, but this doesn't turn this into a density or anything like this. It's really just some normalization. I think is the right way to think about it. Okay, so now we come to the subtlety that Callum mentioned. So commutation relations. Causality. So, we might think we're doing great, that we've managed to rewrite our theory in a way that looks completely Lorentz invariant, because the operators now depend on space and time and obey this Klein-Gordon equation, which is Lorentz invariant. But there's a small subtlety which is in the commutation relations that that the operators obey. So in the Schrödinger picture, the operators obeyed certain commutation relations, but there's no mention of time. So what are the commutation relations when we go to the Heisenberg picture? Well, we could always pick a time where the Heisenberg picture and the Schrödinger picture agree. And so we can carry over the commutation relations at a fixed time. So the fields now obey equal time commutation relations. Okay, so x and y are different, but the times are the same. We've got no information at the moment to tell us how an operator at this time, at one time, interacts with an operator at a different time. Okay, so we've still got this slight residue of the fact that we weren't working in a manifestly covariant or Lorentz invariant fashion, lurking in the commutation relations here. Okay. So what about operators at arbitrary space-time separations? Okay, so here's the kind of familiar light cone we draw in general relativity. Let's suppose there's some operator O1 inserted here, and some other operator O2, which we're going to take outside the light cone. And we want to know what happens, what's the commutation relationship between O1 and O2. We know that if O2 sits here on this axis, then the two commute unless x is equal to y, so unless they coincide. But if this is to be a Lorentz invariant theory, it better be that O2 commutes with O1 if it sits anywhere outside the light cone, because another observer, of course, would have this as his t-axis and should find that it commutes. Yeah?
So can we use that, though, just to write this out and if that's Lorentz invariant, then can we say we just shift to a frame where the t coordinates are the same for space-wide and apply that formula?
So you could, but you might be nervous that you're sort of screwed up in going through the calculations. So as it turns out, we haven't screwed up, but it's an important lesson in quantum field theory. If you've had to take a route through your calculations that's required at some point that you kind of forget a symmetry's there and make your equations make your equations look as if the symmetry is broken, there's a very good chance that your symmetry is actually broken and won't be restored at the end of the day. So there's a whole beautiful story of something called anomalies in quantum field, where you think your theory has a symmetry, but you can't figure out how to calculate keeping that symmetry, so you get rid of it and think it's going to turn up at the end of the day, and it doesn't. And these are real physical effects. They're responsible for the lifetime of the pi zero meson. Takes the value it is because a particular symmetry that you thought was there is not. Yeah, so yes, you could do that, but it's always best to check in quantum field theory to make sure that your equation, your theory really does have the symmetry that you think it does. Otherwise, you'll be bitten. Yeah. So we're going to do that now. Are there any other questions? So we would really like So in particular for causality, it's kind of crucial that any two operators, O1 and O2, that are separated by space-like distances commute with each other. Okay, this is the statement that a measurement here can't affect, or certainly can't signal to any measurement here. Yeah? I mean, now we're in the Heisenberg picture. All operators depend on both space and time. So x and y is a 4-vector in space. So it's an operator at this point.
So perhaps I'm thinking about this completely wrong. I could easily write down, for example, like the total momentum operator for the field.
Right, so that's not a localized operator. That's
okay, so what do you,
that's
not the question. And what do you mean by localized operator?
I mean the kind of thing we've been dealing with all week. It's an operator which is a function of space and time, and so it's the operator evaluates it.
I mean, again, I could write all of my momentum operators are functions of like p.
No, that's right. So in that case, you're giving an example where you're integrating local operators over space.
Well,
look at the thing you're integrating. That's what I mean by local operation.
Do you want that to be x squared minus y squared, or x minus y quantity squared?
Okay, so this ensures the measurement of y not signal to the measurement of x. Okay, so is it true? And let's just check. We're going to define the following. So you could look at so you could look at phi and pi, but actually the thing that's going to be more interesting in what follows is to actually look at phi commutated with phi. Okay. Again, there's no guarantee that this commutes. We know that there are equal time commutation relations, so that phi evaluated at a time t, but any space point, does commute with another phi evaluated at time t. So the only thing we know is that phi of xt and phi of yt is 0. But now we want to evaluate this when the time here and the time there can be different. So one can check that. Okay, and you all know what this means, right? It means homework. Delta x minus y Okay, so again, simple calculation, plug in the mode expansions, do the commutations, there'll be delta functions from the commutations, and this is what you get, okay? Okay, so things to note. You know, in principle, what appeared on the right-hand side should have been an operator, because the definition of this guy is an operator. But what actually appeared on the right-hand side is a very simple operator. It's just a number. Okay, this is just an integral of c numbers, so it's the operator 1 multiplied by this number. Okay. Again, this is something that will be true in free theories, but typically not true in interacting theories if you consider same commutation relations. Okay.
C number complex?
Yeah.
Okay.
Yeah. You just need a normal number.
Classical. Classical.
Is that what it stands for?
Yeah, the Q numbers are the operators.
Good. Good. It's the thing that we know in high school. Okay, the next thing to notice is that it's Lorentz invariant. Okay, so that's very good. Why is it Lorentz invariant? Well, here we've got 4 vectors dotted into each other, so this is Lorentz invariant. Here we may have to worry because it's the integral over 3 momentum, but this is exactly the factor in the measure which makes this the Lorentz invariant measure. Okay, we proved that at the beginning of the lecture. So it's Lorentz invariant. It doesn't vanish for time-like separated events. So for example, if x minus y is equal to t 0, 0, 0, which means that the operator O2 is inserted within the light cone of operator O1, so you wouldn't expect there's any reason they commute. Certainly they can, measurements done at O1 can interfere with measurements done at O2. So if we evaluate the following, you can just see that it goes roughly takes the following form. Okay, so it's not equal to 0. But finally, it does vanish at space-like separation. So why does it vanish at space-like separation? Well, now we're just dealing with an ordinary function. We don't have to worry about any subtleties. And it vanishes because we know it vanishes when we're at equal times. And it's a Lorentz invariant quantity. Therefore, it has to vanish if we do any Lorentz transformation on it, where they're separated outside the light cone. So it vanishes at equal times. And is Lorentz invariant. Okay, so it's taken us a bit of work. We butchered this theory so much to go from Lagrangians to Hamiltonians that after we quantized, we had to work kind of hard to make sure that everything was still Lorentz invariant. The fields obey Lorentz invariant equations of motion, the operator fields, and the operators have commutation relations which vanish whenever they're at space-like separations, which you need for any kind of causality to work. Tibra.
What about light-like separation?
In this theory, I'm not sure. Typically, if your theory has a massive particle, it certainly won't vanish. Here, the theory has a massive particle. It's worth checking.
Well, by Lorentz invariance, can you just move the point back to the origin? Just to brand at the same time and the same x tilde, x tilde.
I suspect not.
Isn't x minus y always 0 then?
X minus y is certainly always 0. Yeah, I don't think there's a Lorentz transformation which really brings that all the way down to the origin. You want to boost sort of a light-like direction and yeah, arbitrarily close, so not right there.
And x is y, x minus y is 0, doesn't the integral just vanish?
X minus y squared.
Oh, squared.
Other questions? All good? Okay, stay on.